Before we journey into the strange and wonderful world of quantum computing, let's take a moment to appreciate the marvels we already have. The device you are using right now, whether it's a smartphone, a laptop, or a desktop computer, is a classical computer. It's a machine built on a very simple yet powerful idea. At its heart, it's a universe of switches, billions of them, all flipping on and off with incredible speed. These switches are called transistors, and they are the fundamental building blocks of our digital age. They are the neurons of the electronic brain that powers so much of our modern civilization. These tiny switches work with a language of just two words, on and off. We represent these two states with numbers, 1 for on and 0 for off. This is the binary system, the alphabet of every classical computer. Each 1 or 0 is called a bit, which is short for binary digit. Think of it like a light switch. It can either be on or it can be off. There is no in between. Every single thing your computer does, from displaying this text to playing a video or sending an email, is ultimately broken down into a long sequence of these ones and zeros, these simple bits of information. Imagine a vast library, but instead of books filled with letters, every single volume is filled with endless pages of ones and zeros. That's what the memory of your computer is like. Each photograph, each song, each document is a unique pattern of these bits. To process this information, the computer's central processing unit, or CPU, reads and manipulates these bits according to a set of instructions, which we call software. It is an incredibly efficient system, a testament to human ingenuity, capable of performing billions of calculations every single second, all by flipping those tiny, reliable switches. But what if there was another way? What if information wasn't limited to just on or off? What if a single unit of information could be both on and off at the same time? This question doesn't make much sense in our everyday world of light switches and clear-cut answers. But the universe, on its smallest scales, doesn't play by our everyday rules. To understand the next great leap in computation, we have to leave the familiar world of classical physics behind and venture into the mysterious, counterintuitive, and utterly fascinating domain of the quantum realm. Welcome to the quantum world. Down here, at the level of atoms and particles, the rules of reality get wonderfully weird. Things are no longer solid and definite. Instead, they exist in a haze of possibilities, a cloud of potential. An electron, for example, isn't just in one specific place. It exists in many possible locations at once until we measure it. This is the strange logic that governs the very fabric of the cosmos. It's a place where particles can be in multiple states simultaneously and can be mysteriously linked across vast distances. It's this very strangeness that we are learning to harness. Now imagine we could build a computer that operates using these quantum rules. Instead of bits that are either 1 or 0, this new computer would use something that can be both 1 and 0 at the same time. We call this new unit of information a qubit, short for quantum bit. A qubit isn't a simple switch, it's more like a spinning coin just before it lands. While it's spinning, it's not quite heads and it's not quite tails. It's a mixture of both possibilities. Only when we stop the spin and look, when we measure it, does it finally choose a side and land on either heads, which is 0, or tails, which is 1. This ability to exist in multiple states at once is a quantum property called superposition. It's one of the key ingredients that gives quantum computers their extraordinary power. A classical bit can hold one piece of information at a time, a 1 or a 0. But a single qubit, thanks to superposition, can hold both a 1 and a 0 simultaneously. It lives in a richer, more complex reality. It's not just a single note, but a chord containing multiple notes at once. This fundamental difference is what sets the stage for a computational revolution unlike any we have ever seen. So a quantum computer is not just a faster version of the computers we have today. It is a completely different kind of machine, built on a completely different understanding of the universe. It doesn't rely on simple on or off switches. Instead, it manipulates the delicate probabilistic nature of matter and energy at the atomic scale. It computes with clouds of possibility, exploring a vast landscape of potential answers all at once. This is a machine that speaks the native language of the universe itself, the language of quantum mechanics. Let's really unpack the difference between a classical bit and a quantum qubit. Imagine you have a single light switch. It can be off, which is 0, or on, which is 1. That's 1 bit. If you have 2 light switches, you have 4 possible combinations, both off, which is 0, 0, first off and second on, which is 0, 1, first on and second off, which is 1, 0, or both on, which is 1, 1. A classical computer has to check each of these combinations one at a time. To represent these 4 states, it needs 2 bits. This is a very linear, step-by-step process. The computer can only be in one of these 4 states at any given moment. Now, let's think about qubits. If you have 1 qubit, it can be a 0, a 1, or a superposition of both. But the real magic happens when you add a second qubit. With 2 qubits, you don't just get 4 possibilities that you have to check one by one. Instead, the 2 qubits can represent all 4 of those combinations, 0, 0, 0, 1, 1, 0, and 1, 1, simultaneously. It's not just one of them, it's a quantum mixture of all of them at once. This is a profound leap in information density. A 2-qubit system embodies a complexity that a 2-bit system can only describe sequentially. The power scales up exponentially. A classical computer with 3 bits can be in one of 8. That's 2 to the power of 3, combinations at a time. But a quantum computer with 3 qubits can be in a superposition of all 8 combinations at once. With just 300 qubits, a quantum computer could represent more possible combinations than there are atoms in the entire observable universe. This is a number so vast, so mind-bogglingly large, that no classical computer, no matter how big or powerful, could ever hope to handle it. It's like comparing a single path to a landscape of infinite branching trails, all explored at the same time. This exponential power is why quantum computers aren't just about speed, they're about complexity. For certain types of problems, a classical computer would need to grind through every single possibility, one after the other, a process that could take billions of years. A quantum computer, by holding all the possibilities in superposition at once, can essentially look at the entire problem landscape in a single glance. It can find the patterns and solutions hidden within that immense complexity in a fraction of the time. It's a fundamentally different, more holistic way of computing. Let's explore superposition with another analogy. Imagine you're trying to find your way out of a giant maze. A classical computer is like someone walking through the maze. It tries one path, hits a dead end, turns back and tries another. It has to explore every single path one by one until it finds the exit. If the maze is incredibly complex, with millions of possible routes, this process could take an extremely long time. The classical approach is methodical and reliable, but for truly enormous mazes, it's just too slow to be practical. A quantum computer using qubits in superposition is like flooding the entire maze with water at once. The water flows down every single path and explores every possible corridor simultaneously. It doesn't have to choose a path, it takes them all. By observing where the water flows out first, you can instantly identify the shortest path to the exit. This is a simplified view, of course, but it captures the essence of quantum parallelism. The computer evaluates a huge number of possibilities at the same time, not sequentially but all together in one grand quantum calculation. This is not just a theoretical trick, it's a property we can control. Scientists use precisely tuned lasers or magnetic fields to nudge qubits into a state of superposition. It's like perfectly spinning that coin and keeping it spinning. They can then perform operations that affect all the possible states, the 0 and the 1 aspects of the qubit at the same time. The calculation evolves, with all the possibilities interfering with each other, much like waves on a pond. The right answers are amplified by constructive interference, while the wrong answers are cancelled out by destructive interference. When the calculation is complete, we perform a measurement. This is the moment the spinning coin finally lands. The superposition collapses and the qubit settles into a single, definite state, either a 0 or a 1. Because of the clever quantum interference we engineered, the state it lands on is highly likely to be the answer we're looking for. We might have to run the calculation a few times to be sure, but it's still astronomically faster than checking every possibility one by one. It's a probabilistic, yet incredibly powerful way to find a needle in a cosmic haystack. As if superposition wasn't strange enough, the quantum world has another trick up its sleeve, one that Albert Einstein famously called spooky action at a distance. This phenomenon is called quantum entanglement. Imagine you have two qubits that are created in a special, linked way. They become entangled. From that moment on, their fates are intertwined, no matter how far apart they are separated. They could be in the same lab or on opposite sides of the galaxy, and the connection would remain instant and unbreakable. They become a single, unified quantum system. Here's how it works. Let's say our two entangled qubits are set up so that if one is measured as a 0, the other one must instantly become a 1. And if the first is measured as a 1, the second must instantly become a 0. Before we measure them, neither qubit has a definite state. They are both in a superposition of 0 and 1. But the moment we measure the first qubit, and it chooses to be, say, a 0, we know with absolute certainty that its entangled partner, even if it's light years away, has instantly become a 1. This isn't communication in the classical sense. No information is traveling faster than light. Instead, it's a fundamental correlation built into the very fabric of their existence. It's as if you had two magic coins. You give one to a friend who travels to Mars. You flip your coin in New York and it lands on heads. You instantly know that your friend's coin, when flipped, will land on tails. The outcome wasn't determined until the moment of the flip, but the correlation was always there. Entanglement is a deeper, more mysterious kind of connection that links the destinies of particles. In a quantum computer, entanglement is a crucial resource. It allows us to create powerful correlations between qubits. By entangling multiple qubits, we create a complex computational space where the state of one qubit is directly related to the states of many others. This allows for more sophisticated algorithms and more powerful information processing. It weaves the individual qubits together into a single, powerful tapestry, where an operation on one part of the system can influence the entire thing. It's this spooky connection that helps unlock the full potential of quantum computation. So, what are these massively complex problems that quantum computers are so well suited to solve? They aren't going to make your video games run better or your web pages load faster. That's not their purpose. Their true calling lies in solving a special class of problems known as intractable problems for classical computers. These are problems where the number of possible solutions grows exponentially with the size of the problem. For a classical machine, they quickly become impossible to solve in any reasonable amount of time, even if you had a computer the size of a planet. One famous example is factoring large numbers. It's a simple task to multiply two large prime numbers together. But if you are only given the result, trying to find the two original prime numbers, the factors, is incredibly difficult. Our modern digital security, the encryption that protects your bank account and online messages, is built on this very difficulty. A classical computer would have to try dividing by every possible number, a process that could take thousands of years for the numbers used in today's cryptography. It's a computational brick wall. A quantum computer, however, could use a special program called Shor's algorithm to find those factors with relative ease. By leveraging superposition and interference, it could test all the potential factors in a way that reveals the correct answer exponentially faster. This has profound implications for cybersecurity. While it could break our current encryption methods, it also paves the way for new quantum-proof methods of securing information. It presents both a challenge and an opportunity to build a more secure digital future, one based on the laws of quantum physics itself. Another area is optimization. Think of a delivery company trying to find the most efficient route for its trucks to visit hundreds of cities. The number of possible routes is astronomical. This is known as the traveling salesman problem. A classical computer struggles with this, often settling for a good enough route rather than the perfect one. A quantum computer could explore the vast landscape of all possible routes simultaneously, identifying the truly optimal solution. This could revolutionize logistics, finance, and engineering, saving immense amounts of time, fuel, and money. The potential applications of this quantum power extend far beyond mathematics and logistics. They touch upon some of the most fundamental and challenging questions in science and technology. One of the most promising fields is medicine and materials science. Molecules, after all, are quantum systems. The way drugs interact with proteins in our body is governed by the complex laws of quantum mechanics. Simulating these interactions accurately on a classical computer is incredibly difficult because molecules are too complex. A quantum computer, however, speaks the same language as the molecules it's trying to simulate. It could model chemical reactions with perfect accuracy. This would allow us to design new drugs and therapies from the ground up, tailored to specific diseases with unprecedented precision. We could create new catalysts to make industrial processes more efficient, or design novel materials with incredible properties, like room temperature superconductors that could lead to lossless power grids and ultra-fast magnetic levitation trains. It's like having a perfect virtual laboratory to invent the materials of the future. Quantum computing could also revolutionize our ability to understand and predict complex systems, like the Earth's climate. Weather forecasting and climate modeling involve an immense number of variables, from ocean currents to atmospheric chemistry. Even with our most powerful supercomputers, we are limited in the accuracy and timescale of our predictions. A quantum computer could handle this complexity, allowing for more precise models that could help us better understand climate change, predict extreme weather events with greater warning, and develop more effective strategies for protecting our planet. The quest for knowledge itself will be transformed. In fields like cosmology and particle physics, scientists grapple with enormous datasets and incredibly complex quantum theories. Quantum computers could become essential tools for sifting through this data, finding the subtle patterns that lead to new discoveries. They could help us simulate the conditions of the early universe or probe the mysteries of black holes. Quantum computing is not just a new tool for calculation, it's a new window into the workings of the cosmos, from the smallest particles to the largest structures in space. If quantum computers are so powerful, why don't we all have one on our desks? The simple answer is that building and controlling them is one of the greatest scientific and engineering challenges of our time. Qubits are incredibly fragile. They exist in a delicate quantum state that can be easily disturbed by the slightest interaction with the outside world. A tiny vibration, a stray magnetic field, or even a small change in temperature can be enough to knock a qubit out of its superposition, a process called decoherence. This decoherence destroys the quantum information and ruins the calculation. To prevent this, quantum computers must be kept in highly controlled environments. They are often housed in large, elaborate refrigerators that cool the quantum chip down to temperatures colder than deep space, just a fraction of a degree above absolute zero. This extreme cold helps to minimize thermal vibrations and keep the qubits stable long enough to perform a calculation. This need for extreme isolation makes today's quantum computers large, expensive, and complex machines confined to specialized laboratories. Another major challenge is error correction. Because qubits are so sensitive, errors are common. A quantum calculation can be thrown off course by decoherence or imperfect control. Scientists are developing sophisticated quantum error correction codes, which use multiple physical qubits to represent a single, more robust logical qubit. This is like having backup copies of your information, but it requires a huge overhead of extra qubits. Building a fault-tolerant quantum computer, one that can correct its own errors, will likely require hundreds or even thousands of physical qubits for every single logical qubit. Finally, we are still in the early days of writing the software, the algorithms, that will run on these machines. Thinking in terms of superposition and entanglement requires a completely new mindset and a new mathematical language. Researchers around the world are exploring new quantum algorithms to tackle different kinds of problems. We are like the pioneers of the classical computing era in the 1940s and 50s, building the fundamental tools and discovering the basic principles of a new kind of information processing. The journey is long, but every step brings us closer to unlocking this new frontier. We stand today at a remarkable moment in history at the dawn of the quantum age. The journey from classical bits to quantum qubits is more than just a technological upgrade. It represents a fundamental shift in our relationship with information and with reality itself. For centuries, we have built tools that operate according to the familiar rules of the world we can see and touch. Now we are learning to build tools that operate according to the deeper, stranger, and more powerful rules of the unseen quantum realm. This is a leap as profound as the discovery of fire or the invention of the wheel. The impact of this revolution will be felt across all of human endeavor. It promises to give us the keys to unlock a new era of scientific discovery, allowing us to design life-saving drugs, create revolutionary new materials, and develop sustainable energy solutions. It could help us solve some of humanity's most pressing problems, from fighting disease to mitigating climate change. The possibilities are as vast as the quantum landscape itself, a space of nearly infinite potential that we are only just beginning to explore. The world of tomorrow may be built on the foundations of quantum computation. Of course, the path forward is filled with immense challenges. Building stable, large-scale, fault-tolerant quantum computers will require decades of dedicated research and brilliant innovation. We are still at the very beginning of this journey. The quantum computers of today are like the Wright brothers' first airplane, a groundbreaking proof of concept, but a far cry from the jumbo jets that now circle the globe. Yet that first flight changed the world forever, and so too will the mastery of the qubit. The challenge is great, but the drive to explore, to understand, and to build is a fundamental part of who we are. So, the next time you look up at the night sky and ponder the mysteries of the cosmos, remember that the same strange quantum laws that govern the stars are being harnessed right here on Earth. We are learning to compute with the fabric of reality itself. Quantum computing is a testament to our relentless curiosity, our desire to peel back the layers of the universe and understand its deepest secrets. The future is not just something that happens to us, it is something we build. And right now, in labs around the world, we are building a future that is truly quantum.